very excited to talk to you about image analysis on high performance computing. And I'm also want to immediately express that I'm here, joined by Benjamin Pavie, who will try to do some live demos with. I have a slide a bit later on this because I wanted to actually start with why we're doing this. Because technically, I think that we all know we face the problems that data sets are getting bigger and analysis is getting more complex. So in a way, we may face some bottlenecks sooner or later anyway. And I think for that, definitely the writing is on the wall. There is more multimodality imaging and more like that. And then I would just argue that creating scalable and reproducible image analysis workflows that are fair, we started with fair, is actually something that should be dear to all our hearts. So an entertaining question is, how do we work with the scalability aspect? So here, eventually, working with a high performance computing center is an opportunity for scalability. But obviously it comes with a price and we need to see a bit how this goes. And here I want to make a bit of a case on how we interact here, in our case, Flanders Bioimaging, with the Flemish Supercomputing Center and how this has been working for us. Maybe as an extended motivation, during last year, there was a Globias meeting in Gothenburg, and we inquired also there about the high performance computing situation with bioimage analysts. So in a way, I thought you may have seen this or some have seen this, but maybe our audience may be a bit broader and a bit bigger. I see we are 106 folks online. So I want to quickly share what was the outcome for one of the questions where we asked, do you have access to high performance computing? And there was a big consensus on that. A lot of people actually do have access, but a question on what is holding people back is a lot of knowledge. For some, it's obviously the infrastructure itself, it's lack of training, and some other options that are also listed here. So I felt we could try to, bridge this gap a bit by actually explaining how we have tackled this, how this is going at our side. And I would actually love to even discuss this a bit further at the end of this session here on how what's your interest and how we could, broaden this further. I realize this is not obviously a proper training, so you likely will not. So here, disclaimer, sorry for that. You will likely not get out and know exactly how to run your cluster. Likely, I'm also not the best person for this in any case, but what I thought is actually to try to bring up a few things that can be actually, help and actually starting that dialogue and then seeing also what we would need for actually making some more practical training for that happen. Specifically, if we look beyond our own landscape and here addressing the bigger Euro-BioImaging community. So, but first, my shout out goes out to the people that actually made that presentation possible. On the one hand side, there is Tatiana, who actually shares her greetings. So the picture shows her. It's the one that makes the heart for you. But she is now having an immersive experience, if I may call it like that, and is not going to join. But we have here Benjamin, who is also on a different event because he's dialing in from the update on the data carpentry, which is currently in parallel happening at the IST. So this is a bit unfortunate because I think there might be actually a pool of people who actually couldn't make it here because of that clash. Benjamin, as good as he is able to do both. So he's here joining here while he's actually in at the IST dialing in. So I blame the IST if later demos don't work because they may have cut the cord. But in any case, I'm very thankful that Benjamin here joined that, and we will try to actually showcase a few things a bit later. It also means he's not at his regular place, which also means we are accessing our cluster even more remote than regular. So this may actually add a layer of complexity to the whole thing. We only do this for your entertainment, of course, but we'll see how much we laugh at the end of that session. Good. Maybe my last slide on the motivation or to bring up is, or what we can try to solve this in this next minutes here is a bit on the IT lingo, because what I learned is when I talking to the people that run our hardware, it can be a bit of a challenge here. And one part is that it often feels like they're coming with a new tool you have never heard. It's a bit like, talking to someone that, just expresses he found some new Pokemon and you don't know what they're actually doing about. And often the problem is since you don't know what they're talking about, it seems like it may solve all of your problems, but maybe not. So like the unknown Pokemon, it has a hidden power and you don't know what it means. So and therefore, I felt we need to distinguish this and talk a bit about few tools and stuff that are out there and what they can actually handle and solve for us. So let's go easy about that and talk about few things. Maybe to just settle the ground. Let's start with, what is it actually that I'm talking about when I always talk about high performance computing? What does it look like? So it's a small chapter I'm talking about here. At our place, what's the tier system? Because I will come back a bit later, and why this may matter actually for you. So high performance computing, or HPC, means the practice of putting resources together to gain an edge when it comes to performance that would be normally bigger than your single workstation or server or computer that you have. They can come in very various forms. Often they're built around groups of similar items, and then we talk about clusters, and you have a cluster of multiple things. And on these, you can book resources, maybe multiple cores on that, and including, for example, also storage and GPUs and so on. So what is that tier system that I have been talking about? That is something that is used in that field. And typically, we all have experience with tier 3. That is typically your desktop. Then on the university level, you may have individual servers or smaller clusters. That is typically called tier 2. And then there is regional or national kind of facilities. That is tier 1. And this is what I'm talking about mostly. We also use a bit of tier 2 at times for various reasons. When I talk about the supercomputing cluster or the VSC in Flanders. There is also still a level above that. And that's also why I wanted to mention that dedicatively, because there might be opportunities in that sense here, specifically in the context of Euro-BioImaging, where me actually may want to reach out eventually even more, because there is the so-called Euro-HPC joint undertaking, or often abbreviated U or JU. And it's a partnership and for doing advanced computing in Europe. And I will share a very quick summary about it. There's actually way more to talk about, but I felt like this may be, and it's also a reason why we're talking about this stuff here today, opportunities that we actually have that we may have not tapped in entirely, that we can actually maybe use also to our advantage here within Euro-BioImaging. So there is the idea of an European high-performance computing federation platform, and that is built on open source software. So I've been sharing here some quick slides that I took actually here from a colleague who was presenting these. The idea behind that, and I'm not going to talk over this busy slide, is meaning that here basically all of Europe except Andorra and Switzerland has actually joined together to build out this joint initiative to build a world-class supercomputing ecosystem. So you can see already also in the items below that there's actually quite some compute power available. And the entertaining question is, how do we make this more accessible and more easy available for users? And this means us eventually as users. In that federation, there is currently regular so-called classic supercomputers. There's 9 active. There's 3 more planned. They are can be seen by the half red circles. And then there is so-called AI factories that are planned that are meant for AI optimized computing capabilities. They don't exist yet, but they're selected for the end of 24 and will be consecutively built up. There's also some plans for quantum computers at various stages, but you can also see that if we talk about Lumi, for example, that there's actually almost 3,000 GPU nodes available, which means that there's quite some impressive compute power available, and it can be interesting to see how we could potentially leverage that. Now, I'm coming back to us because we are actually Flanders Bioimaging. We are in mixed node, so we combine between preclinical imaging and as well optical imaging. We are in consortium within Flanders, including all 5 universities. And this is us, a happy bunch of people that have been having some networking event last December. And if you compare that now to the Flemish Supercomputing Center that I've been just mentioning, you can immediately see that there's quite some similarities behind it. It's also in partnership of 5 Flemish universities. There is the tier 2 accessible to the individual universities and tier 1 through projects. And I will talk about this a bit later. They provide different services from consultancy to research, collaboration, and trainings. And I will try to fill this in a bit more in detail. You can actually see a picture of the VSC at the bottom. And I will talk in the next moments a bit about our current state of affairs with that. And we want to supplement that a bit with some live demos and core facilities. The VC set up into 3 different parts. There is the compute part, there's the cloud part, and there's the data part. And obviously the compute is parallel processing on the regular, what we normally think of high performance computing environments. Cloud would be to run virtual machines and others kind of stuff. While data is obviously for storing of active data. I will talk about how we actually plan within Flanders Bioimaging to link data and compute a bit later. So when it comes to these 3 services, there is the idea behind that to talk about supercomputing as a service. I think it's actually nice because it brings in the bridge to the beginning of the data community days where Asta was talking about image analysis as a service, and maybe we can think about in the future as supercomputing as a service to image analysis as a service. And we felt that this could be thought of a future backbone for doing image analysis as a service. So how does it look like when we talk about tier 1 compute? In the past, this is our common view about how we thought high performance computing normally looks like. Today, it looks more like this or like this, where we actually have in way different ways to interact with different items. You may already recognize some few tools, and the way that this works is a bit different and than it used to be. I want to give a quick sideline to the band, the image analysis desktop, because this started a bit our interaction as well, because it's a platform that was built out by the EMBL and gave access in a kind of remote desktop style on their cluster to a number of well-known tools. At the moment, as far as I know, it's actually retired at the EMBL, but it's actually resurrected in Tübingen, and there is more possibilities, I think, to do this. And last week or the week before, we were actually talking that people are hopefully starting to use this resource and provide feedback, because this is now a tryout within Euro-BioImaging. In our environment, we don't use the original band. We use something that is called Open on Demand, which is also providing you with a remote desktop. It's called, or it's used, I mean, Open on Demand is a project basically used by quite a lot of different organizations. And it's obviously, it's something that if you would be reaching out to your HPC colleagues, what they would recognize, because it's something that is actually deployed very often, and it would be a way to provide you with a desktop kind of experience in your browser to use it. And it's kind of a way to share different tools. There is a large number of tools already available, and you maybe recognize here, for example, Blender or VS Code or some others that are, already, directly employed, and you can use more of that. In our environment, it runs here on another framework that's called OpenStack, and it gives us a way to run different applications on the high performance computing center. And moving slowly towards a first demo, we have been looking here at the NeuroDesk, which has been recently published. I have shared some links to the NeuroDesk by itself. There's a publication. It runs on Open on Demand at our place, and there's a lot of fields or tools that are actually used in the medical environment. There is Slicer, there's ANS, there's a number of other stuff. You see also there's RStudio and a number of other stuff. But in our environment, we can also use Elastic on the HPC running on Open on Demand. We were here with the intermezzo of the demo, which I'm very glad and relieved to say that it worked well. We had some backup movies, so I will skip over these slides, so don't worry. We had some more of these just to make sure, bring a point across. It also shows you that we can run many different things. I mean, this would have been an Cellpose movie, which we collected before, just to say, like, whether you said like, Napari and Elastic is not my favorite and Stardisk, who knows, but literally it works for many things that you would be liking, presumably. And here, just to reiterate, we have seen the Open on Demand environment, which is, a bit more easy accessible than the regular standard command line type of interface that we've seen. We have been running here Napari from a Singularity container, and just to point out, a container is, Singularity is a container platform, and it will mean that you have put together the software together with its own dependencies and binaries into one file, so that you can run it on different host systems. On HPC, Singularity is preferred for a number of reasons. It also is nice in the fact that you can build it on your laptop as a container and then deploy it, for example, on the cloud, on your workstation down the hall, or on the HPC. And it's a single file that is actually required then for all operating systems, and it's open source. We have seen this. There was a backup movie because obviously we tried to be ready for that. Benjamin has also been showing quickly the easy build. I mean, just to talk about the lingo and what it entails, to say like, yes, here we have a framework that allows you to manage different systems on high performance computing centers. Reason for that is that they don't want you to install every time everything with Conda, but it will clock the system quickly, right? So that's a way to package things together, because they share similar kind of requirements. And like that, it doesn't mean that you cannot have different versions, for example, of Python, but you can have things together that use the same version of Python, and you only have that once, and that's overall more efficient than having it every time reinstalled by every user. And that's why this is a preferred way of interacting. And I felt this would be useful to bring this up when we talk about or when we make this presentation, that people actually know what we're talking about, and also how to talk with your VSC center. So maybe to reiterate, because you have seen it's nice that we can do this, but we can also say or ask, what is the underlying idea? What do we want to achieve? So quick summary of the different ways to interact. We have seen Open on Demand, which will provide you with a virtual desktop sorry for slaughtering words here somewhere. We have seen easy build for an efficient installation framework for running applications, and we have talked a bit about containers to build your own reproducible tool. For us, the idea was, you may need these tools to make your bespoke analysis, but we want to go a step further because we thought when we, interact with the supercomputing center that we could also automate more tools, right? There is also talking about next generation file formats and OMSR on the data community days. So we thought that we could go with something like this, where we, take the data, go to the data part of the VSC, do some regular pre-processing, and then do the dedicated simple or dedicated specific analysis for the individual tools. That's a bit what our roadmap looks like, also to share that. We started obviously earlier, and we wanted to start it with some OMSR testing, and had some entertaining problems with doing so. Currently, we want to get more people in our environment to use it and share this, and in order to roll out more apps on Open on Demand next year, and then consolidate and collect also feedback and roll out analysis as a service throughout. So how does it actually work? Because, obviously you have seen that we can do things and that it worked quite nicely, but how did we get there? Because I mentioned tier 1 is actually project-based. There is tier 2, which is credit-based, which means there is some fee associated at the end. It depends from where you are, how expensive that is. But what does this grant-based actually mean? It means that you actually have to make an argument why you would need tier 1. It also means that you need to deliver, for example, some kind of information on how good your tools are actually running or up to run on high performance computing center. And it means that you need to require some wall time for how fast you can compute things on the resources that are available to you, and provide graphs like, for example, on the efficiency versus the number of cores that you have used. I'm sharing here an example where we used a Nextflow pipeline to run some files to convert them to OMSR. We have been looking at, what works better to concatenate them and then convert them and so on, and to see how efficient it is for that purpose. It doesn't mean that you can't use it when even the most efficient one is to use a single core, but it's also, trying to make best use of the resources that are made available in these computing environments. Which brings me to the fact that, we're already starting to interact between data and compute. And here I want to quickly share how we actually got there, because actually we started from the data part first before we got into the compute part. And we came from the point that, when we don't take care of the data, we actually running into some problem. We, Flanders Bioimaging, want to provide, people with the best data that they can have. And this is, in that sense, the oil that we're pumping. But we also know if we don't take care, we quickly litter the space, and we need to make sure that this is actually not the case. So we want, obviously, fair data handling, but we also want to make sure that things are handled well and end up in the right place in order such that they are indeed findable and reusable at the end. Good. So it started out that there is a cheap storage on-premises cloud, so to say, that has been built. It's built around iRods, which is an environment where open source data management software, if you want, and it's also used widely by data centers. And it means that you actually have to search for your data through some search function. For that, in our environment, a new tool was created that's called Mango, which can be used for metadata creation. It's a metadata schema manager, but it also will handle the upload of the data and also the accessibility of the data. And it can be automated. Since we run a bit short in time, I will skip the fact that we can upload data there. I trust you believe me when I say that we can upload data somewhere. In these times, there would be alternatives. There's stuff like Globus for actually doing this kind of things as well. And like I mentioned, it can be used to run or create metadata, and we can annotate basically data ad hoc and just add new fields and edit them and add some information if we want. Here's a quick example running where we add a lens to a system. There is a mini schema that has been created, but this could be your RAMBI schema or your based one on the bioimage archive. Now, the entertaining part that we wanted to do is connecting the data and the compute bits, because here we deploy or envision that we wanted to connect data from the microscopes, load them up into the data repositories, and have them there available to do some analysis. And this is the scheme that we created. And as you can see, it's terribly busy and very complex. So I tried to actually summarize this a bit and make it more simple, but you see that a number of the tools that we have been talking about have been just coming back. It starts with the fact that we have the instrument where you either manually or more automatically upload stuff, and I talk about this in a second, where you then can do analysis, either offline or online. I want to have a quick point on that as well, because here we can do more automation than what you have seen so far, and we can end up with depositing things on institutional repositories. So manual upload, you have seen a quick movie starting on that works with Mango. But now more interesting is that we can think about some automatic upload. And what you see here is a quick movie. If it starts running, actually. And here it goes. It actually is, that's the screen of one of our microscopes. So you can see here, this is actually images that I acquired a bit ago, last August, apparently. And then you can start a tool to actually load them into our Mango system. You would need to authentify for that purpose. So here you get a QR code with your phone in order to identify yourself. This is the regular procedure at our case. And then you can say here, we want to start uploading things automatically, and it will be just creating an immediate mini metadata schema based on where you have been, on which microscope you have been logging in, on who you are, on which room you are located, and these kind of stuff, and we'll start uploading that. The movie you will see is actually way longer, because it will now show you in a second how we actually observe that it actually works, but there's nothing more required than actually providing maybe an email so that you can be notified when your data is finished with the upload. And it will do this in the background, and will just have you to select that scheme and do the upload. So you're technically done at this point. And you can see there's a JSON file created for that purpose. And we're going here a bit too lengthily about this fact by actually showing where this is going, and that we can now actually investigate that the machine is doing something in the background. It's running. You can see that the Ethernet is actually active and doing this technically. The idea behind this, while this is actually taking too long, is that we can set up some way to automatically in the background overnight have a process that is scheduled to run and upload the data, and that at some moment it will be just done. You get a notification for that purpose, and then you have created a data repository on the iRods together with some mini metadata schema that you then need to annotate further. And here you can see, just if you look at that, you can see that this has been actually uploaded and worked fine. Good. So while we actually currently, this is work in progress, and it means actually that we need to start training people new for this purpose, but this is part of a new workflow, how we start using our environment for that purpose. And it means also that we can prevent clocking our local hard drives, and we have a process in place where this is actually happening and where we can work with that. Now we can do some high performance computing analysis with these data, and I will skip fastly through this, but we can also use some Python API to actually reconnect to our work, to our Mongo, to actually also add metadata from the analysis to that process. This can end with the fact that we can also load this up to some local data repository. In our case, this is called the radar. That's a KU Leuven local one. But we could also make that happen for the bioimage archive because it means that only the JSON file from the Mongo would need to convert it to a JSON compatible one from the bioimage archive. Now you have seen we have a nice schema in place and it looks hopefully reasonably useful. But the idea is actually to step this up even one step further and actually use this possibility that we can automatically upload the data and have it available in a data center further. That we can actually use this for that pre-processing steps that we had in mind. What we need for that is a so-called scron job. It works. The idea is that we have the data and a scheduled system behind it that would use some processing script, for example, and carry this out on the high performance computing. I've showed this data schema before where we go from the data conversion to pre-processing to analysis, and this would be solving the pre-processing for that purpose. And just to explain this a bit more, a cron job is a regular Unix command, a Linux command that can be used for scheduling tasks. And scron job is a similar thing, but targeted for Slurm clusters and will be just doing also a scheduled task. And we can set this up. And you can see this here in the movie, in the sideline. It's way too complex. I will skip over that quickly, but you can actually use it as a metadata flag to say, like, please convert this data to OMSR, and this movie will be just running in the background, and you need some configuration, which we try to streamline at this moment. So this is admittedly still work in progress, but the whole point is that we have created and managed workflow where you can go from an upload to metadata scheme to use tools like Open on Demand and related to the analysis and to the full circle to the repository and go from transfer, research data management over analysis to the deposition of the data, all based on open source in a complete workflow from acquisition to publishing. And most importantly, that is data agnostic, putting different pieces that are actually all out there together in one item. And for that here, I want to point out that in our environment here, this Mongo tool has been quite important. And this also gives you the possibility to also use this further and mine your data for any future AI applications that you may have in mind. We have prototyped this at some moment where we looked at connections between ELN entries and also from connecting it with publication data to get some structured output, for example, to read how well contained is metadata resources, for example, in the Mongo versus the ELN versus a publication. I will, this has been published earlier, so I will not talk about this long. I will just start wrapping up here, saying that this is a work in progress. And it could be interesting to also see how we as Euro-BioImaging can maybe connect to the European level of the high performance computing. And I want to quickly summarize. A lot of what I've showed is work in progress. I hope to convince you with the help of Benjamin that we can actually use a lot of these cool stuff already at our fingertips. And I think that is something that you can also do. Here, the interaction and with the IT is obviously key. But automation and scale up possibilities here is a large opportunity that I think we want to are an opportunity to use, and many of the tools are actually already available. It's making that happen. There's also some considerations to make. There's the downside that you may have to queue. It's not a resource that you have always available. as running an bioimaging core is also something that we tell our users that you have to book the system eventually. Currently, you're typically placed in the queue. That's often a bit different than booking it and knowing when you have it available. So there's some differences that are actually important to consider. The interaction can still be different, right? I mean, we have seen this also in the demo a bit. It also more and more uncoupling eventually your analysis and your acquisition parts, right? This can be tricky for specifically for some of the image acquisitions that require some direct processing. And because you're missing the feedback, did this actually work well? I don't want to say that I/O bandwidth issues can be real. I mean, we have seen this now here halfway across Europe working quite well, which I think is cool and impressive. But if you need to upload your data set, this may still be a burden at times and may take a while. So this needs to be something that you also need to be aware of. It also means if we use this as, for example, providing access for, analysis as a service, it means it's not your infrastructure. You're using, the HPC as a subcontractor. This is something important to recognize that, I mean, we also don't build our own microscopes all the time, so that's also important. But it's just to make this explicit, right? Good. Coming back to how I started, we had that training question, right? I mean, before, what is people keeping you from using it? And we also had a question back in autumn. Are courses for image analysis on high performance computing missing? A large number of people here answered with yes. Now, if I look at our environment, our supercomputing center provides a number of trainings. We started to create our own course, bioimage analysis on high performance computing. But it will mean that you will be trained targeted on the specificities of our own Flemish supercomputing center. Here, I'm not 100% sure, and this is a bit where I want to actually start having a bit of feedback, and maybe someone has some idea about it. Would you be interested about that, right? I mean, because you will be at home facing slightly different challenges. You may have the skills, but it's not like, it's not a turnkey system. Now you have got the training and now you can use it because your environment will have a few different things. Obviously, it can be used, or we are happy to be used also to say, like, look, this works with those. I mean, why can't we have this? This sometimes works with people. IT can be stubborn. We don't know exactly. But the question that I have to you is, we are not the only ones who created a course like that. Just to point out, the CRIC has also created a course for using Open on Demand and Introduction to HPC. And here, I would love to have your feedback maybe in the last 3 minutes or so. Would you be interested in, for example, our course or the CRIC? Or shall we try to set up a connected course? But then we actually may need some help because it's not an European project immediately. Because if we want to use LUMI, the European infrastructure, we may need a European project for that, though Euro-BioImaging is one. So maybe we may need here some help and maybe we can put this together. But then I don't know if people would be interested. We are happy to train you also on our HPC. They're always a bit picky that we get if someone comes from Australia, getting them the number to actually have access. But we will manage. I mean, but the case that I want to make is how would that work for you? Would you be interested in that? And shall we try to pull this off?